I'm going to talk about a different problem, which is about optimizing ad yield on Spotify platform, which is very important for actually serving music for a lot of our free users. So basically, this talk is going to focus a little bit. It's going to be mostly like a case study presenting how we built a forecasting system for the ads platform. And I'm going to talk about the different approaches that we thought about, how we ended up building the system, and some key takeaways. So my name is Kinshuk, and I've been working on distributed systems and data science problems at Spotify, and I've been focusing mostly on the ads platform over the past couple of years. For those of you who don't know about Spotify, we are a digital music streaming service, and we started back in 2006 and launched in the US just over 2 years ago. Currently, we have over 24 million active users, out of which 6 million users are paying users. So we are a freemium tier. We have a freemium model where we have both the free tier, which is supported by ads, and a premium tier where you can get an ads-free experience by paying a monthly subscription fee. As of today, we are available in about 28 countries, and we have over 300 engineers, out of which nearly 100 of them work in New York. So why are ads really important for Spotify? And the reason, as you saw in the previous slide, is that most of our users who actively use our service are actually free users, and ads help us pay for the music that they consume. As of today, Spotify's paid hundreds of millions back in royalties to music labels, and ads definitely help support that particular purpose. In addition to that, ads are also a great medium for promotion and announcements. So whenever there's a new artist launching an album or something like that, we also use ads platform to serve those kind of notifications. One of the key things that we like to we care about is serving like premium branded experiences on Spotify. We've been thinking a lot along the lines of coming up with native ads which look and feel more like the content on our platform. So they are not really intrusive, and this is an example of a music album promotion. So to get this kind of branded experience, what's really important for us is to ensure that the production quality of ads is really good, and that for those reasons we typically engage in direct sales of our ads. So what that means is basically we have an in-house ads sales team which actually talks to media agencies and different brands and tries to sell ads to them. So that leads me to the problem that I'm going to talk about. The problem is basically of optimizing the yield of ads on Spotify platform. Now, whenever our ad sales team, or the folks from that team, go and talk to brands, what we want to make sure is that we are not overselling ads on our platform, because that would mean that we won't be able to satisfy the quotas that we've reserved for each of those campaigns. But at the same time, we don't want to undersell ads, because that's like leaving money on the table. So we want to have the right estimate of amount of ad impressions that we can serve on our platform. So to solve that particular problem, the type of questions typically folks in ad operations or ad sales have is along the lines of something like this. Like, given a particular targeting criteria, for a specific type of ad on a specific platform for a given date range, in certain metro areas, for certain kind of demographics, how many ad impressions can we serve? And in addition to this, there are a few other metrics that they care about, like the reach of a campaign and so on and so forth. So this problem that that I'm talking about is not necessarily very unique, because there are a bunch of ad tech companies out there who've solved this problem in the past. But there are a few things which are unique about our platform which does not help enable us to sort of get an off-the-shelf solution and use it directly. A few of the things which are unique are the way we trigger ad breaks on our platform. So the audio ads themselves are not very common in the industry, the way we have them on our platform, and they're actually pretty important for us because they're native to our platform, we being a music platform. And the rules that trigger those ad breaks are pretty unique, so we really need to capture those, that kind of logic in our system, in our forecasting system, to actually predict how many ad impressions do we have. But in addition to that, we also have some interesting data set. Typically, ad tech companies use log-level ad impression data to predict the ad inventory for the future. But we also capture a lot of interesting data about users' audio streaming activity, data about how they're actually interacting with the platform. And there are ways in which we can actually use some of this data to predict the number of ad impressions for a future campaign. Now, given that we have these kind of data sets, what are some of the different approaches that we thought about before we started implementing this system? So one approach which we actually even tried in the past, and we again thought about it, was actually simulating the delivery of different ad campaigns by replaying the user events and triggering ad breaks. So that would effectively mean that you try and simulate an ad and see how it plays, and that would actually give you some sort of estimate of how many impressions can be served. Another method is to actually pre-compute aggregates along different dimensions. So let's say the total number of impressions for a particular gender, for a particular location, and then build complex models for combining those different aggregates. And another approach that we thought about was basically just using the raw impression data as is, and then apply different kinds of filters based on different targeting criteria, and then use some extrapolation to actually, using some simple model to actually give the total number of ad impressions that we could have in the future. So having thought about a few of these approaches, we wanted to evaluate, does our infrastructure actually support this? So for the size of the company we have a pretty good in-house Hadoop infrastructure. We have about 700 nodes in our cluster, and we typically run jobs on top of this infrastructure using streaming jobs or Hive. And there are ways we could have just run this in a batch mode and computed those results. But we had some constraints from the product side. We wanted to build an engine which was a fast real-time lookup service. So the traffickers didn't have the patience to, or whenever they're doing some kind of business, they really don't want to wait for a batch job to complete. So they really wanted something which is fast and they can just look up these values in real time. They wanted the results of a forecast to be consistent. So for the same targeting criteria, if they run forecast one after the other, the results shouldn't vary a lot. They should pretty much be consistent. We wanted our system to have the ability to add additional targeting in the future. So as we keep improving the ad experience, we want to sort of have hyper-targeting features built in our ad server, but at the same time have the ability in our forecasting system to add those additional targeting features. And lastly, we wanted the system to scale. So with the growth in the number of users and with addition of new targeting features, we didn't want our system to sort of be limited in what it can do. So having described the different approaches and the constraints that we had, the first approach of simulating all the events doesn't really help us solve the problem in real time. So, let's actually take a look at those constraints. So the first approach sort of does not help us build something which is real time. The second approach of actually rolling up aggregates around different dimensions and then combining them using a complex model is somewhat complex to debug, and adding any additional targeting features can be a bit complicated. And also building complex models in our experience hasn't scaled that well. So the solution was to actually choose something which could scale pretty well and satisfy all those criteria. So we went for the third approach of actually using a subset of impressions and applying different filters and extrapolating it. But how did we actually solve that? So let's go to the fun part of actually diving deep into this problem. When we started building the system, we thought this is what the big picture of the whole system is going to look like. We store all the log level data in our on HDFS in our Hadoop cluster. So we are going to get some of that data from our Hadoop cluster. All our booked campaigns, which give us the number of booked impressions for that date in future, is going to be pulled from a Postgres database. And we're going to feed those values into a forecasting engine. And whenever it gets a query, it could run a forecast. At a very high level, we thought the forecasting engine would have an algorithm something like this. Basically, we would have a cache of data loading data sets from Hadoop and from Postgres database. And whenever, once the data was loaded, basically, on submission of a query, we would apply different filtration criteria based on targeting information that has been provided. Then we'll count all the available impressions and apply a bunch of growth and other extrapolation factors to make sure that the results can give the values for the total population. So what were some of the challenges? Like any other data set, our data set had some challenges as well. A few of those challenges were organic growth in inventory, the problem of cold start, and seasonality. So I'll talk about each of these problems in a bit. So the first problem was the problem of capturing organic growth in our inventory. So this is a graph. For obvious reasons, I've removed the y-axis because those numbers are sensitive. But this is a graph of the total impressions that we have for one of the growing markets. So as you can see, over time, as people start using our service, there's a lot more activity, and we have a lot many impressions on our platform. So we need to capture these kind of trends to make sure that our estimates for future are accurate. But at times, the growth is not necessarily positive. It can be negative as well. The good news is that this is not due to the bad performance of Spotify platform. This is just because in one of our mature markets, a lot of our users are actually starting to like our service, and they're converting from free tier to the premium tier. So the actual ad inventory is reducing. So we also need to be careful about capturing these kind of trends when we're making any sort of predictions. The problem of cold start. So whenever we are launching our service in a new market or a country, we really don't have any kind of data about the previous usage. So a good technique that we've used is basically using a proxy data set. So let's say a country A is where we're going to launch our service, and it has resemblance to some country B where we've launched in the past. We can use that data set as a proxy to sort of make estimates for country A. And lastly, the problem of seasonality. So this is a graph which represents in one of the markets, we see dip in the ad inventory during early parts of Q1. And some of the reasons for that are that until recently, we didn't have a good free tier mobile offering, and most of our users were using our application on desktop. So during that time frame when they're traveling around, there's a lot less activity and our inventory size reduces. And also the data sort of represents the actual ad delivery, and the reason we see a dip in that delivery is because the spend during the early parts of Q1 on ads reduces, and it's very high during Q4. So these were the data challenges, and I'm going to talk about how we actually addressed few of those. But there's another constraint that we need to think about, or it's more of a design decision. But given the volume of the data that we have, how much of the data should we use for actually making accurate forecasts? We serve we serve billions of impressions per month, and we have terabytes of relevant forecasting data. But if we want to use that and feed it into a system which is going to be real time, it's going to be really challenging. So some of the basic techniques that you can use are like sampling from a population. Using any of the standard hashing mechanisms, we use MD5, which give you uniform and consistent distribution. You take the whole population and choose a sample from that which is representative of the population, and actually run experiments on that particular sample, and then extrapolate the results. After running few experiments, we found that the data set size which works for us is a data set for the past 1 month. And we use that data set to make predictions for any date in the future. So the way, one interesting problem that I wanted to highlight was how we actually load the data from logs, which is daily data, is basically on the first load of the cache, we actually load all the past 31 days. And on the subsequent reloads, since we have a different thread which basically creates a different copy of the cache, and we maintain atomic reference to the old copy, we add the data for the new day and remove the data from the old day in the copy of the cache. And basically once this is done, we swap the references. Since the references are atomic, our data set remains consistent. And we keep doing this on a daily basis. So we don't have to restart the service every day as we do that. Another thing which we wanted to focus on was making sure that the data retrieval is really optimal. Since we wanted the service to be real time, we focus on the kind of data structures we chose. Before making sure that the data retrieval is really good and performant, we analyzed what are the different data access patterns. What we found was that on most occasions, about 75% of the times, the campaigns that were being trafficked on our platform were targeted mostly by age and location. So we made sure that we maintain a quick sort of lookup map of this information, so that whenever we are actually reading this information from the cache, the access is really quick. So what this helps us in is we maintain a sorted set multi-map, and the service being in Java, we use Google's Guava library, and we use this particular data structure which helps us maintain a location-wise list of users which are sorted by their ages. So now our lookups are really optimized by a factor of log n, because instead of retrieving the list of the users and iterating over them, now we're just, we have the sorted list, and we can select a particular age group which satisfies the criteria. The way we are using a month's data is basically in this manner. So we do a substitution of a day of a month with the previous day of the month. And to illustrate that, basically, so let's say today is 13th of September. And if I want to make a forecast for today, based on historic data, I'll use 13th of August as my reference point. So basically, if you see those two green bars, the one on the right for the 32nd day is actually a replica of the first day. And we've accounted for some growth in our inventory, and we add that to actually represent the total inventory for that day for a particular user. So I'm going to run through the algorithm in pretty much how it actually goes and gets the final values. So we basically take all the user add impressions by applying day of the month substitution, and this is again working on the sample of population, not the whole population. Then we apply all the filters based on the targeting criteria and make sure that from the population, from the sample of the population, we are choosing only those data points which actually match the targeting criteria. So we start adding these filters. Once we get all those users, we basically just count the total number of impressions for all those users, and we get the total number of impressions available to actually serve ads. From that, we subtract, or rather, we also read the booked impressions from the Postgres database, and then we subtract that from the total impressions to actually give us the total available inventory. I'm going to talk a little bit about the growth factor. So based on the different, the organic growth or sometimes the negative growth, we want to capture the trends in those things and apply it towards the end to our results. So we ran through different models and found that typically for most cases, keeping a simple model really helps us capture the growth trends, and also the time it takes to build these models is really small, so it scales pretty well. And we didn't have to go for very complex models for capturing those data trends. So typically, it's a good idea to keep your trends very simple if it allows scalability. So all our calculations were actually on a population sample. So to get the final value, we want to make sure that we also scale it back to the actual size. And this is an example of how you would do that. So basically, if you've scaled down your sample from the population by a factor of 100, you want to add multiply that back to the answer that you've received from the previous step and get the basically the total inventory. In addition to this particular forecast, we've added a bunch of other features which are very non-standard and not available in off-the-shelf solutions, which is like capping the frequency of ads that you receive and doing a bunch of other filtrations. So in this whole approach, what are the things that worked really good for us? One was that we definitely built a service which actually enabled us to have fast lookups. Our simple models scaled well. They didn't take a lot of time, and they were easy to understand. We used a lot of deterministic algorithms because they help debugging they make debugging very easy. Because in the past, we've had some randomizations introduced in our models, and that sort of makes it difficult to figure out whether the problem is in the data set or is it just some randomization. Given this approach, adding new targeting features were easy because they're pretty much a new filter that we apply in our algorithm. And since we are not doing any simulations, our forecasting engine is pretty much agnostic to the way ad server works. So any change in the rules of ad server do not affect us that much. The things that didn't really work that well for us were basically the campaign level forecasts, because without running actually a simulation and trying to figure out what's the pacing of a particular campaign, how the pricing affects the delivery, making any forecasts for campaign can be really difficult. Cold start is a real problem if you do not have a proxy data set. And again, for new ad types without any data set, it can be challenging to do any forecasts. So what we've learned is basically that when you're trying to build something similar, you should think about the data volume, consider sampling and choosing the right time window. You should definitely try and understand the data access patterns and optimize for that. Try and use deterministic algorithms. and basically build simple models that scale really well. That's it, thanks. And one last shameless plugin. We are hiring for all kinds of engineers, so if you're interested in any of the problems that we're trying to solve, you can subscribe to the Spotify jobs handle. Thank you.